So this one's really easy for anybody to understand, right? So you put 100 in, it bounces back, okay, with 33. So I still have 33 moving in the universe here. So if it was in a sealed container, you could understand. I have 100 going this way. Now I have 33 heading for this wall, and I have 133 heading for the other wall. And that's not a 100%, a 60% increase in the energy in the system? Of course it is.
If you have a minus 33 and a plus 133, they
Right, and somehow the energy knows which one to minus. Yeah, so I have a plus 33 and I have a minus 133. And I end up with a minus 100 then. Cool, I have minus 100. I mean, you could just ask the question, why is the reflection a minus? Okay, it's just as capable of hitting something. The one going to the left is just as capable of hitting a wall and breaking something. Too stupid. You know, our minus 100. Fuck your stupid brain.
Okay, so imagine that we are in space. We are inside the vacuum of space. We have our card 1. Okay, and we have card 2 with so 1 mass, 2 mass. The initial momentum of card 2 is 0 and the momentum of card 1 is 100 going to the right. So they are about to collide. After collision, what happens? Mass 1 will obviously reflect back, and theoretically with momentum, well, if it is 10 meters per second, I believe if it's coming with 10 meters per second, its momentum will be, what is it, 130, I'm sorry, minus 33, and this one, so to the left, this one will bounce back to the left, of course. This one will have momentum of 133 to the right. Now, according to ref science, yeah, he will say we have 33 extra momentum this way and 33 extra momentum this way. So a total of 166. We have 66 extra momentum of free momentum because the initial momentum was only 100. But what ref science never does, he never consider the fact that when we talk about conservation of momentum, we are talking about the system as a whole. The system as a whole. The system as a whole. Because if we are in space, the system as a whole is also moving to the right in this particular case. It's moving to this side. Okay? This one is stationary and this one has 100 momentum, right? What will happen is this one will go to the right, this one will go to the left, but at the same time, the system as a whole is also moving to the right. Okay? Let's say these are the cards. This is 2 mass, 1 mass. This one is stationary. This one is coming in, right? And after collision, they reflect and they move this one to the left, this one to the right, but at the same time the whole thing is moving to the right as well. So what happens is the motion of this card, of card 1, all right, he has motion to the left, but at the same time motion to the right, and that's the point where we can talk about cancellation of motion. It's the same. I have shown you the example of a person standing on a treadmill. If the treadmill is moving to the right with a velocity of 5 meters per second, and the person is moving to the left at the same time with also a velocity of 5 meters per second, then his net motion is 0. He isn't going anywhere with respect to the frame of reference of space itself. He isn't going anywhere. Yes, he's moving, he's actually moving to the left, but at the same time he has motion, he has exactly the same motion to the right, so he isn't going anywhere. His net motion is 0 meters per second. So in the same way, this one has motion to the left, but at the same time is going to the right. So he's going to have a net motion. And so the net motion of the system as a whole, is going to the left with momentum of 33, but at the same time it's going to the right with momentum of 133. And so its net motion is going to be 100 to this direction. Okay? This is not free momentum. This is the momentum of the system as a whole. And it's the same as before collision. The momentum before and after collision of the system as a whole is conserved. So again, the negative sign doesn't mean that this is anti-momentum or cancellation, that the momentum actually doesn't exist anymore. It's just we are talking about the amount of motion in a direction, the quantity of motion in a certain direction. So I can go a certain quantity of motion in this direction, let's say with 10, but at the same time, so in this case, and at the same time I can go with a quantity of motion to the left with 100, and so what will happen is, what will be the net result if I'm going with a quantity of motion with 10 to the right, but at the same time with a quantity of motion with 100 to the left? What will be my net motion? Will I go to the right or to the left? Well, I will go to the left, but with how many quantity of motions? Yes, 90. That is going to be my net momentum, my net quantity momentum to the left. That's what it means. That's why we have to subtract momentum, because it's quantity of motion in a direction. After collision, the system has to go somewhere, either to the left, to the right, or above, below. But in this case, we're talking about left and right. That's the whole fucking thing that you don't seem to understand. That's momentum. That's quantity of motion. Direction is crucial. That's why we subtract. Okay. If I'm going 10 to the right, but at the same time I'm going 100 to the left, a quantity of motion with 10 to the right and a quantity of motion with 100 to the left, what will be the end result? Well, I'm going to the left with a quantity of motion of 90. That's why we have to do 100 minus 10. That's going to be my net momentum, my net motion to the left. For fuck. Will you ever get this?